Hi everyone. Today we are going to talk about another topic in deep learning, which is vanishing and exploding gradients. So let's begin. So as you can see in the slide, the first thing that we need to talk about is vanishing gradients. Exploding gradients has similar concept, so we need to be very conscious while discussing vanishing gradients. The similar concept will apply there as well in exploding gradients. So in case of vanishing gradients, as the term vanishing is there in it, it means that something is disappearing. Now, what is disappearing? Gradients are disappearing. Internally or indirectly, we can say the gradient values are becoming so small that we can say they are disappearing. So where are these gradient values used? Now we already know in case of gradient descent algorithm, this is the formula which is given for weight updation. So new weight is equal to old weight minus learning rate into an error gradient with respect to the weight. Here we are using the error gradient. Now if the values of gradient will become very, very small or very minute, in that case, the update of the weight will be very minute. And if that is the case, we will see that the minima is achieved very late, or it just keeps on going in a loop without even achieving the global minima. That's because the updates or weights on top of the weights are not even happening. It feels like the update is maybe 0.00000001. So that is equivalent to no update on the weight, which in turn causes no convergence or no global minima achieved. So let's see another equation below. So just concentrate on these three figures. So this will help you understand why gradients are or gradients value are becoming very low, or why it is affecting the network. So if you multiply two numbers which are in decimals between 0 to 1, the output number is lesser than both of the numbers. Here we are multiplying 0.2 and 0.3. The output is 0.06, which is quite lower than both of these numbers, 0.2 and 0.3. Same way, if we multiply any decimal number between 0 to 1 with integer, it makes the value of integer to reduce to a larger extent. So 0.2 into 3 is equal to 30 is equal to 15. But if the numbers both are integers, then the value is bigger than both the numbers. Another concept to learn or to understand before going forward with vanishing gradients is this block diagram below, or this image below. There are some activation functions like tanh and sigmoid. So here we have shown sigmoid for an example, whose derivative is lesser than them. For example, here the sigmoid graph is shown as a S-shaped curve here. But when we take the derivative of a sigmoid, we get a normal distribution. We get a distribution as shown below with the top value as 0.25. So this is the concept that we need to understand the value of vanishing gradients. Now let's try to understand this architecture here. Even though this is not very deep network, but let's say we are looking at a smaller piece of a 100 or a 200 layer network. We cannot show all of those layers here, but let's just assume it's a 100 layer network and we are just looking at a smaller piece of that network. Now what I need you to concentrate is two things. When we calculate the gradient of error with respect to W23, what would be the path followed? This is the output error that will be computed on y bar or y hat. So your gradient of error with respect to W23 will follow path as follows. It will start from E, it will go to the y hat, then it will go to Z51, and then it will go to W23. On the contrary, when we want to go to, let's say, W17, the gradient of error with respect to W17 will have additional parameters in its computation, which will be A41 and Z41 along with W17. So what I'm talking about, let's see the equation. So error gradient with respect to W23, let's look at the bottom one first, is error derivative of error with respect to with respect to activation of the last layer, which is the y hat. Partial derivative of y hat or activation of the last layer with respect to the z value of the last layer into partial derivative of the z value of the last layer with respect to the w value in the second last layer. So that's error gradient with respect to W23. But when we look at error gradient with respect to W17, we see that there are more terms which are getting added as a part of the chain rule in this computation. Now, when we add more and more computation factors to this equation, one thing which will come into play is how many of these factors are between 0 to 1. We need to remember this equation here. If both of the numbers or more the numbers are between 0 to 1, decimal numbers between 0 and 1, they are going to bring down the final value always. So here both of the numbers are less than 1 or 0 to 1, in between 0 to 1, they brought down the value down like anything. If one of the number is between 0 to 1, it will still bring down the value of the other number. The same concept applies here. The second thing that we remember from the previous slide is that a sigmoid function's derivative is quite low, between 0 to 0.25. And here we have a derivative of activation function. So that means we are using, let's say, sigmoid here. So this term would be really low, between 0 to 0.25. Again, we have a derivative of activation of fourth layer with respect to the z value. So this value also will be very low, between 0 to 0.25 in case of a sigmoid activation. So two values we are very sure will be between 0 to 0.25 in this computation. Now, if weights are also quite low, then this will bring down the overall value quite low, which means the error gradient with respect to W17 is going to be very low, which will make the update of the weight based on the gradient descent formula very low. That means the weights are not changing sufficient enough to achieve the global minimum. Now, if you look at the below equation, the number of multiplicative terms in this equation are less. And it is the gradient of error with respect to W3, the effect of vanishing gradient or the effect of the sigmoid function will be very low here because the number of multiplicative terms are very less in the computation of error gradient with respect to W23. Right, so basically we understood that sigmoid function or a tan H function is a culprit, is one of the culprit here that can cause vanishing gradient. So how do we take over or how do we avoid this? Let's avoid sigmoid function in these scenarios in deeper networks. So what do? We used ReLU function instead. But ReLU also has a problem. ReLU will make all the values lesser than 0 equal to 0. So if you're passing a value -2, it will default it to 0. Right? So in some of the cases, an entire node or an entire computation will become 0. That is the situation of dead ReLU. But that can also be taken care by using leaky ReLU. So overall, we can say that one of the reasons that can cause vanishing gradient, which is a sigmoid activation function, there are ways to accommodate that, or there are ways to overcome that by using other activation functions like leaky ReLU or ReLU activation function. Let's look at another reason that can be caused, that can be the reason for vanishing gradient. Now you see this architecture here. This is the binary classification architecture, a very basic architecture. Now, what I have done here is I have given you some equations which are for error gradient with respect to W5 and how it is computed in this network. W5 is this one. So the gradient of error with respect to W5, it will be computed based on two paths. The error will go from the end to E1 to A31 to Z31 to W5. And there is no way that we can reach from E2 to W5, right? So there's only one way to reach to W5, which is by following E, then E1, then A31, then Z31, and then W5. So gradient of error with respect to W5 would be the addition of gradient of E1 with respect to W5 and the gradient of E2 with respect to W5. The gradient of E2 with respect to W5 will become 0 because there is no way we can reach W5 from E2. And now we will compute gradient of E1 with respect to W5. E1 has this equation in case of a binary classification network. So it is a generic log loss kind of a formula. So minus y log y predicted. And we have just plugged in the value minus y1 log of y predicted. Y predicted is A31. So y predicted is the last value here of activation in the last layer, A31. Now we compute the gradient or the partial derivative of this. That comes out minus y1 by A31. The second term is activation's partial derivative, and the partial derivative of the activation in case of sigmoid function will be between 0 to 0.25. The last term is partial derivative of Z31 with respect to W5. Z31's equation with respect to forward propagation is given here. Z31 is equal to W5A21 plus W6A22. This is a basic forward propagation equation that you can easily compute. If we take a partial derivative of this equation with respect to W5, we will get the output as W5. Now you have come up to this equation. One piece which we have already seen in the before slide, in the prior slide, is the importance or is the reason number one, which is the use of sigmoid activation function, because the derivative of a sigmoid activation function will be between 0 and 0.25. That will bring down the overall computation very low. The other piece which is also present in this computation is W5 or the weight. That means if we increase the weight or we decrease the weight, that also will have an impact on the gradients. If we decrease the weight or if we keep the value of weights very low, that can also cause vanishing gradient problem. So that is the reason two that can cause a vanishing gradient problem, and it can be overcome by using the proper weight initialization strategies, which we will be discussing in later sessions. So till now we've discussed about vanishing gradients. The similar kind of concept applies to exploding gradients. In vanishing gradient, we discussed that the weight values could be very low. That could be leading to a vanishing gradient. Now let's assume the weight values are really, really high. So then that could cause an exploding gradient. And in case of exploding gradient, the global minima will also be delayed as well. I mean, we will not be able to achieve the global minima fast. That is because your output will keep on revolving or will keep on stepping further towards one side from the minima, and then again it will come back to the other side, but it will not go down to the error minimum. This is because your weight updates are very high and your gradients are also very high. They're exploding. Every update that you do to the network is quite high. Now, how can you control this kind of thing? The simplest way to control this kind of thing is to reduce the error, to reduce the learning rate. So if you remember the equation of gradient descent, that has learning rate also involved. If you keep the value of learning rate very low, it will accommodate for the higher weights that are there in the network. But the other two major things that can help prevent this kind of issue is gradient scaling and gradient clipping. First thing which is simple to talk about is clipping. It's very simple. So you have a gradient value which is beyond a certain range. So let's say we define a range of -5 to +5, plus 0.5. Any gradient value which is above 0.5 is defaulted to 0.5. Any value which is less than -0.5 is defaulted to -0.5. That's all about it, gradient clipping. An example is given here of a network. So you're using SGD. And if you see here, we've given a parameter called as clip value equal to 0.5. That means the value or the threshold should be between -0.5 to +0.5. The other issue or the other way that we can deal with exploding gradients, it's gradient scaling. As the name determines, it is gradient scaling. That means scaling the values of the gradients in the network. So what we do, basically for let's say one layer, we get all the gradient values for all the samples in the network. We find the normalized or the L2 norm or the second level norm of the error gradients. If it is greater than a threshold, let's say we have given a threshold as 1 here. So if the L2 norm is greater than 1, then what we do is we scale all the values or normalize all the values of the gradient terms in the L2 norms in such a way that your L2 norm becomes 1. So basically you are scaling the values, you are normalizing, you are standardizing the values which are used for gradients in such a way that they don't really explode or they don't really deviate highly. Right? So that was about exploding gradients. It's a brief idea that has been given to you. Feel free to comment if you have any queries on this. Thank you all. Have a good day. Bye-bye.